Okay, so we'll continue on here. Yeah, what's up?
When you record, you can put them on the test website?
Yeah, they're on the website. Last week's lecture is up. Okay, you guys should have seen it, right? I'm getting head nods, so they're up there. Okay, so we'll continue on. We'll do another example here with hypothesis tests here. Okay. All right, so we'll say last year a study revealed that 18% of students who enter high school do not finish. Okay. Again, I'm just making up these numbers. I don't know if this is actually what's happening. All right. So we'll just say last year's study revealed that 18% of students who enter high school do not finish. Okay. A school district or a campaign to finish high school is implemented. All right. And I'll say after the campaign, a study is done. A random survey is taken, or a random sample is taken of 1,000 randomly selected students 210 not 210, I'm sorry. 155 do not finish high school. Okay. Does this provide evidence that a lower percentage of students drop out? Okay, so this is our question, and we'll answer this using a hypothesis testing approach. Okay, so let's set up our hypotheses. Okay, we have a null hypothesis and an alternative hypothesis. Notice that I'm using colons here and not equal signs. Okay, and the null hypothesis is always about the population, so we're always going to use a p when we're dealing with proportions, never p hat. So the null hypothesis is that nothing has changed from last year. Okay, because the question here is, does this provide evidence that a lower percentage of students drop out? Well, lower than what? Lower than 18%, okay? Because last year we found that 18% of students drop out. And this year we want to know, after the campaign, do fewer students drop out? So the alternative is that P is less than 18%, okay? So a few things to note. In the hypotheses, you use the same number here, okay? use the same number in the null and alternative. Can you guys read that? Good. Okay. And again, always use P. So I'm just annotating this. For proportions, always use P. We will learn other hypotheses tests where we are dealing with means. But for proportions, we will always use P. Okay. And then the null always has an equal sign. Okay, so let's answer this. So we want to know, if the null hypothesis is true, what's the probability of us observing this? Our data. What is our data? Our data is 155 out of 1,000 drop out. Okay? So we need to establish what n and what p hat are. What is n? 1,000. What's p hat? 155 over 1,000, 0.155. Okay? And we want to figure out what is the probability of this happening if our null hypothesis were true. So if the null hypothesis were true, we would expect it to be 18%. What did we observe? 0.155, okay? So we want to know what's the probability of this happening, or something more extreme, something more unusual. So we got to figure out what is my standard error, and we're going to use that to get our z-score. So the standard error will be, what do I put in there? P. So do I use 0.155 or 0.18? 0.18, okay, times 1 minus 0.18 divided by 1,000. Okay, and so punching this into my calculator, 0.18 times 1 minus 0.18 divided by 1,000. And I'm going to take the square root of that, square root of the answer. And I get my standard error is, whoops, 0.01215, okay? 0.01215. That's my standard error. My z-score is going to be what? 0.155 minus 0.18 divided by the standard error, 0.01215. Okay, so 0.155 minus 0.18 divided by the answer here. I get a z-score of negative 2.06. I'm going to look this up in the z table. Look up negative 2.06. And I get 0.0197. When I look this up in the table, the area is 0.0197. Okay, this area is known as my p-value. Is 0.0197. So does that seem likely or unlikely? Unlikely, okay? So rule of thumb, not always, is if it's smaller than 0.05, okay? We set something called alpha is equal to 0.05. And if the p-value is smaller than 0.05, in general, we would say it's unlikely. Okay, so if the p-value is less than alpha, we say it is unlikely. And if the p-value is greater than alpha, we'll say not unlikely. You guys all have that all down? No? I'll give you a moment to keep writing then. We okay? All right, so in our last, we had a p-value of 0.0197, okay? And p-value is equal to 0.0197, okay? So 0.0197 is less than 0.05, so we say our data is unlikely to occur by random chance under the null hypothesis. Okay. So what this is saying is that if the high school dropout rate did not change, if the high school dropout rate is still 18%, what is the probability that a random sample would show a dropout rate of only 15.5%? Well, it's unlikely for a random sample to show 15.5%. That only happens about 2% of the time. So we either can say it happened by random chance, or we'd say, well, I don't think I'm part of that 2% of weird random samples. This gives me evidence that the proportion we see today is not 18%. Okay, so we would say, so because it's unlikely our p-value is small, we would say we reject the null hypothesis because our p-value is small. Okay. We have reason to believe that the proportion of students who do not finish high school is now less than 18%. Okay, so again, just a reminder, the null hypothesis said that p is equal to 0.18. The alternative was that p is less than 0.18. Our data was p hat is equal to 0.155. Okay, we asked, how likely is it for a random sample to have p hat equal to 0.155 if the population is still 0.18. Okay, The answer? Unlikely. Unlikely. Only 0.0197. So we say the population is no longer 0.18. Good? Yeah? It, I guess that's, I'll take it. Yes. I'm so sorry?
Is the quiz going to have similar problems like this?
I'm not going to have you write all of this verb stuff out, but yeah, you will have questions like this.
Doesn't it actually seem like there are different ways of answering the same question? Is that what it is?
Different ways of answering the same question, but the concept is still the same.
Right.
Okay? Yeah.
But I mean, do you think which
The exact wording, I don't care about the exact wording as long as the concept is correct. And now, sometimes I'll have students turn in responses that I can see where they're coming from, but they're saying the wrong thing. Okay, so what I've written here, even though they're phrased a little bit different, they're all saying the same thing, and they're all valid statements to make. Okay. All right. So I'm going to expand the hypothesis test to accommodate for 2 samples. Okay. Now, the formulas for the standard error and things like that get more complicated, but the overall concept behind the hypothesis test remains the same. Okay, so don't freak out, don't get angry. I'm gonna show you something. Okay, and it's just the concepts remain the same, but the formulas just get ugly. Okay, all right. So this is hypothesis test. Everybody smile. All right. Hypothesis test. For proportions for 2 samples, okay? Previously, you had a hypothesis test for proportions for 1 sample. Okay, now we're dealing with 2 samples. Okay. So your hypotheses, your null hypothesis, well, this is one nice thing. Your null hypothesis null hypothesis H0 is always, okay, is always going to be P1 minus P2 is equal to 0, okay? Or it could also be written, this is saying the exact same thing, is that P1 is equal to P2, okay? Your null hypothesis will always be this, okay? These 2 things, it's going to be this or this. These 2 things are exactly the same thing, okay? They're just written in different forms. Can you guys see that algebraically? Okay? These 2 things are saying the exact same thing, so it's just, this is your null hypothesis, always, okay? The alternative hypothesis will be P1 minus P2 doesn't equal 0, or P1 minus P2 greater than 0, or P1 minus P2 less than 0, okay? Depending on how the question is written. Okay, and their equivalent this way would be P1 doesn't equal P2. These two things say exactly the same thing, so just be comfortable. This is just from algebra though, right? I mean, I shouldn't have to say that these two things are equivalent, but students always get thrown off, so these are all equivalent, okay? So you might see it written one way or another, okay? They're all the same. Okay. That's how the hypotheses are set up, okay? Basically, you are saying, what we're asking is, I have one sample over here, another sample over here. Based on what we see in the samples, does that mean the two populations have the same percentage or not, okay? And we could say, questions that can be answered with this is, does the population of males and population of females have the same percentage of left-handed people? Okay. Or do they have the same percentage of, people who watch soap operas? Does anyone still watch soaps? All right. Or whatever, whatever thing you want to talk about, okay? We're asking, do these two populations have the same, does the population of, I don't know, teenagers have the same percentage as the population of adults who do whatever, okay? You're asking about two groups, and you're asking, do they have the same percentage that have this trait, okay? That's what we're asking in a hypothesis test for proportion of two samples. You've got two populations, and you want to know, do they have the same percentage of something, okay? That's what we want to know. So let's look at how we would do this. Okay, so your data will consist of two samples. You will have sample 1 and sample 2. So let's just say sample 1 will be the males, and sample 2 will be the females. The label of the samples doesn't matter. I could just as easily call sample 1 females and sample 2 males. It doesn't matter. It's an arbitrary choice, okay? But once you make that choice, stick with it, okay? So both samples are going to have a sample size, and to distinguish between the sample size n for sample 1 and n for sample 2, I'm going to put n1 and n2, okay? So n1, let's say we surveyed 80 males, and n2, let's say we surveyed 100 females, okay? X, this will be our count. Let's say out of 80 males, let's say 10 are left-handed. Okay? And for the females, how many left-handed females out of 100 do we have? We'll say 16. 16 are left-handed. Okay? Does this provide evidence? Okay, so for the males, what is the proportion who are left-handed? P hat 1 would be 10 divided by 80. What is that proportion? If you divide it out, you get 0.125. P2 hat, 16 out of 100, 0.16. Okay, so when we look at our two samples, they have different proportions of left-handed people. Okay, so our samples do not have the same proportion of left-handed people. We want to know, does this provide evidence that the proportion is different in the populations? Or the proportions are different in the populations. Okay, so if this is the data, these are randomly selected samples. If 12.5% of men selected in our sample are left-handed and 16% of women in our sample in our selected sample are left-handed, does this mean that overall men and women have a different proportion of left-handed people? That's what we want to know. Okay? So what would our hypotheses be? Our null hypothesis, I said, was always going to be what? P1 minus P2 equal to 0. What is this saying? This says that the two proportions are the same, that P1 minus P2, that there's no difference between the two proportions. And then the alternative would be that P1 minus P2 doesn't equal 0, okay? So this says the proportions are the same. And this is the proportions are different. Proportions of left-handed people. Oops. Hey guys, did you guys get that copied down? Just a second. I'm running out of time. No. Okay. There I go. So those are our hypotheses. Let's talk about how we would solve this, okay? So just like before, I've got a thing, a sampling distribution. In the middle, I'm going to put 0 because in our null hypothesis, we had P1 minus P2 equal to 0, right? You don't have to rewrite this in your notes. I'm just putting this so we have it here. Okay, you don't have to rewrite P1 minus P2 equals 0. In our data, the data that we had was that, and again, you don't have to rewrite the data here because we had n is equal to 8, n1 and n2 equal to 100, and then p hat 1 was equal to, x1 was equal to 10, p hat 1 was equal to 0.125, x2 was equal to 16, and p2 hat is equal to 0.16, right? Okay, so our z-score is going to equal P1 hat minus P2 hat divided by our standard error. And our standard error, this is where things get ugly, okay? It's just this ugly formula. There's nothing we can do about it. We just have to live with this, all right? So don't get mad at me, all right? P hat times 1 minus P hat times 1 over n1 plus 1 over n2, and p hat itself is equal to x1 plus x2 divided by the quantity n1 plus n2, okay? That's it. This is the worst part. It's just this ugly formula, but it's not that terrible, okay? You have to figure all of this, and you plug it in here, and then you get a z-score, okay? The concept is exactly the same as before. It's just the calculations just get a little bit ugly. Okay, that's all. It's not so awful. All right, so let me just show you what we have to do. So first you have to do this. Okay, so this is step 1. And then once you get that, do step 2. Don't try to do this without doing this, okay? So step 1, let's get p hat. So p hat is x1. What is x1 in my data? X1 is 10 plus x2, which is 16, divided by n1, 80 plus n2, 100, okay? Now, it's important, add the numerator. 10 plus 16 is 26, divided by 100 plus 80, okay? Do not, okay? Let me just write a warning here. Do not do 10 over 80 plus 16 over 100, okay? This is wrong, okay? Do not do this. How do I say this is wrong? It's 26 over 180. Very big difference, very big difference. Don't do this. Okay, so what's 26 over 180? 0.144444. Okay, and now that we have that, then we plug it into right there. Okay, so I'm going to have the square root of 0.1444 times 1 minus 0.1444 times 1 over, what's n1? 80 plus 1 over n2, 100. Okay, is that all right? Huh? Where did I get what? Yeah, okay. Okay, so I'm just going to plug this in now. I'm going to do that times 1 minus 0.1444 times 1 over 80 plus, 1 over 100. Parentheses, end. And then I'm going to take the square root of that, and I get 0.0527 as my standard error. Okay? So that is my standard error. Okay? Don't get lost in the formulas. Overall concept is the same. I'm going to say that over and over and over again because that's the truth. If you can keep track of what you're doing, you'll be okay. So now, all we're going to do is we just plug in the values that we know. What is P1 hat? 0.125. What is P2 hat? 0.16. Divided by my standard error, which is 0.0527. Okay? So the key always, as you're doing your problems, label the numbers that you have. List off N1, X1, P1 hat, N2, X2, P2 hat as you're reading a problem. It's going to make your life so much easier because all you have to do is you just plug your numbers in here, you plug your numbers in here, and you get this, okay? And then you get your z-score. So I'm going to do 0.125 minus 0.16 divided by the standard error, which I actually still have in there. And I get a z-score of negative 0.66. Okay, and so this is where I am. Negative 0.66. And I want to know how much is in my area over here. Okay, so if the percentage of left-handed people for males and females were the same, what's the probability that I get a difference like this? So if I look at negative 0.66, I get 0.2546. Okay, so over here the area is 0.2546. Okay, there is a rule that if you have a not equal sign in your alternative hypothesis, okay? So let me just establish this rule over here. Rule. Okay, so this is what we call two-sided tests. If the alternative hypothesis has not equal sign in it, okay, it is a two-sided test. Okay, and that means your p-value is 2 times the tail area. So in our case, my tail area is 0.2546, so my p-value is going to be 2 times 0.2546, and so I get 0.5092. This is my p-value. So let's put it all together. Can I move to the next slide or no? I'll give you guys another minute to copy this down. Remember, the null hypothesis here says that P1 minus P2 is 0, okay? And what we're doing is we're calculating our p-value, which is the probability of observing our data, or something more extreme, if we assume the null hypothesis were true. So if males and females truly have the same percentage of left-handed people, what's the probability that one random sample would give me 12.5% left-handed people, and the other sample gives me 16% left-handed people, if they have the same percentage? Well, when we do our math, it says something like that happens about 51% of the time, 50.92% of the time, okay? So that happens quite a bit, okay? Getting one sample of 12.5% and another sample that's 16% left-handed. How often does that happen? That happens about half the time. So does that mean our samples are unusual? No, our samples are not unusual under the null hypothesis. So we have no reason to doubt that the null hypothesis is true. It doesn't prove that males and females have the same percentage of left-handed people, but these two samples, where I got 12.5% over here and 16% over here, it casts no doubt on the fact that they might have the same percentage of left-handed people, okay? So let me just write that down, okay? So our p-value is 0.5092, okay? This is large, okay? So we do not reject the null hypothesis, and we would say, even though our two samples have different proportions, of left-handed people, okay, the proportions are not different enough for us to conclude that the populations of men and women have different proportions. Of left-handed people. Okay, so please read through these things. I know you guys are furiously copying all of this stuff down, but please read through it and make sure it makes sense to you, okay? And we will end there tonight.